Okay, so thank you guys for watching. Today we're actually going to start with EDA number 2. So we're actually going to work toward the next problem and the next homework for the design of analog integrated circuits. So what we're going to be looking at today, this document just covers just a little bit of it. We're going to be simulating a differential amplifier, a two-stage differential amplifier. So we have our actual differential amplifier here and then a common source output stage with these dimensions. Then we're also going to simulate the loop gain once we close the loop, and then closed loop gain and closed loop output resistance. So this is going to be some stuff that we haven't done before, and this is going to show you some of the pretty powerful tools that Cadence has to actually simulate stability and things like that. So let's get started by making a new library. So I'm just going to do File, New Library. I'm going to call this one ECE EDA2. And we do want to attach this to an existing technology library. So if I press OK, wait just a moment, it'll give me the option to select the library, and we'll select AMI 06. Press OK. So it's going to be attached to the technology library AMI 06. It's created. Now we don't have any cells or any views, so let's do File, New, and Cell View. Make sure that the correct library is selected, so this is under ECE EDA2. And for this one, instead of just naming this, for example, last time I called it ECE EDA1 schematic. But for this one, I actually want to talk a little bit more about, I guess, the cell structure of this. So I'm actually going to name this after what it is that we're going to be building. So if we take a look at this here, what we're going to be building is this two-stage amplifier. I'm just going to call it an op amp, however. So I'm just going to name this one, the cell, is an op amp, because the cell actually corresponds to what it is that we're making. So this could be op amp, this could be ADC, this could be common source amplifier, it could be all sorts of different things. And then the view is going to be the actual view of it, because it could have a schematic, a layout, a symbol, all sorts of different things. So for now, I'm just going to call this one op amp, and the view is going to be schematic. We want to make sure that the type is selected to be schematic, and then press OK. Now we've got our schematic window open. We can actually start populating it with all the stuff that we need. So if we go take a look back at this file, we can see that there's 1, 2, 3, 4, 5 NMOS transistors, and then 1, 2, 3 PMOS. So I'm just going to go ahead and start off at the very beginning, just try and get it all laid out, and then we can start wiring things together and changing the sizes. So once I'm back on my schematic screen, make sure I'm clicked onto it. I can press I, bring up the instance window. And the library that we're going to be using, you can either click and drop down and look for NCSU analog parts, or you can do what I prefer, and you can just type in NMOS4. So if you need to browse, you can always click the buttons, but I prefer to just type it in once you get familiar with it. If you're not familiar with it, then you can kind of scroll through and see what all they have. But since we've had a little bit of experience with all these parts, we can just type it in. So we're going to be using an NMOS4, and I'm not going to worry about the sizes or anything like that right now, because I just want to get this thing laid out initially. Now for this first transistor over here, this is going to be our current mirror transistor. If we take a look at our schematic window, the schematic on the PDF file has the NMOS transistor facing the different way. So what we're going to do is we're going to come back to our schematic window, open up our add instance window, and we don't want to rotate it. We actually just want to flip it across the y-axis. We're just going to click this sideways button. If I look back, now it's flipped. So I'm just going to put this right here. Now we want to put it back again for these other two, and I'm going to add 2 more of these here and here. Now we have 5 NMOS transistors total. So we have our 3 current mirrors, and then we also have our inputs to the differential amplifier. So let's go ahead and add that here. So I'll add 1 transistor. So we need to flip it sideways once more. I'm just alt-tabbing to get to the windows that I need, and I'll press it one more time. So those are all the NMOS transistors that we're going to need. Now we're also going to end up needing some PMOS transistors as well. So if we take a look at the schematic one more time, it's generally a good idea to pop back and forth to make sure that everything is kind of lining up correctly. We can take a look here at this schematic, and what we can see is that these NMOS transistors, we know that the drain of this NMOS is going to be connected to the drain, or excuse me, the drain of this NMOS down here is going to be connected to the drain of the PMOS M3. Same thing for M2 and M4. So we can kind of design those to make them line up together, and we also know that the gates are going to be connected together as well. So we can take that in mind and try and make everything line up. So if we press I again, instead of NMOS4, we're going to be taking PMOS4. Still want the symbol view. And now, instead of having it facing this way, I'm actually going to place this this PMOS here. That way the gates are facing inward and we can connect them together very easily. And then flip it sideways again for the second PMOS. Now we have one last PMOS to put. This is going to be our common source amplifier PMOS. And we're just going to make sure we're flipped correctly. And we're going to put it kind of here on the output. Okay, so now we've got all of our transistors laid out. We can see that we have eight instances here. And we haven't messed with the sizes or anything like that, but we can go ahead and start connecting things together just to get our schematic going and maybe help make it a little more sense. So we know that all of these PMOS, all of their sources are going to be connected to this VDD. Okay, so they're all going to be connected to the same VDD. Let's go ahead and connect them together. If I press W, that'll bring up the wire tool. And then I can click here, give it a little bit of headroom. And then we can do the same thing, just connect all three of them together. Now, I'm not going to add the actual VDD yet, and you'll see why that is. But we're just going to continue along these lines. So we know that the two gates are connected here. So these M3 and M4, the two gates will be connected. So let's connect those two gates. Now we also know that the gate and drain of M3 are connected together, so M3 will be diode connected. So we can go ahead and connect the drains together here, and then add a route to the drain of M3. So now we have our drains connected together. For M1 and M2, the sources are going to be connected together, so let's connect the sources. And then this connection goes directly to the drain of M5. So let's connect here. I'm sort of speeding through this a little bit more because this is stuff that we've already done. I don't want to have to rehash through everything, but we will, still go step by step. Now, all these current mirrors down here, all of their gates are going to be connected together. So if we connect all of their gates, we can get the current mirrors working again. Now, I am actually going to route mine down this way, and this is just personal preference for me. You're welcome to route it however you want. You just want to make sure that, for example, if you go across the top here, you want to make sure that there is no dot. We don't want these two lines connected together. We only want the gates to be connected together. Now the sources for these three NMOS transistors down here all connect to ground. So we are going to connect them together. Press W again, bring up the wire tool. Oh, didn't quite make it. So bring W again. And we want to make sure that it's set to route. So whenever I right clicked, I'll show you right now, whenever I right click here, that actually changed this draw mode here. We want to make sure it's on route. That'll help keep everything looking the way it should. So let's draw one route all the way to the source of the far PMOS, and then we'll connect these two. Now you'll notice that there's no dot here, so that's a good sign. That means that there is no connection between the two. So between this route, escape here, between this route and this route, there are no connections, which is good. That's what we want to see. Now these bodies down here also need to be connected, so let's go ahead and connect the bodies to ground, because we know this down here is going to be our ground. I sort of messed up, so I don't want this to look how it is right now, so I'm actually going to press S. And S is the stretch tool, so pretty much what that'll do is that'll keep things connected, but it'll allow me to sort of wiggle it around a little bit. Now this one isn't being super intuitive right now, so I might just need to give up on this and bring up the delete tool. Sometimes it's not always going to work out super well, but worst case scenario, you just have to delete and then rewire it. So we're going to connect the bodies all together to ground. Remember, the bodies are going to always be connected to the substrate. In this case, we want our substrate connected to ground. Now, for the PMOS, they're going to be in an N-well, so they're actually going to be connected to VDD. So we're going to connect all of the PMOS bodies to VDD. We need to make sure that we get all of them too. Now, you want to make sure that the default route is going to be, especially in this case, if I press U to undo, the default route, if I just click here to here, it's going to be right over the top, and that doesn't look too good. So what we're going to do is I'm going to bring it out and then bring it over. Okay, now we still have some routes left to make. So let's take a look here. If we take a look at the schematic, we know that our output of the differential amplifier goes to the gate of M8. So let's connect those together. We know that the drain of M8 connects to the drain of M7, so let's connect those two. Now, there is something that I'm forgetting. So right now I'm just going to bring some wires out for these inputs here. But there is still something that I'm forgetting. And it's not these inputs. It's not to add the ground or VDD or anything like that. We haven't gotten to that point yet. But there are 2 pins that aren't connected. And if I save and check, it will give me a lot of warnings because there's lots of stuff that's left unconnected. For example, these pins here. Let's actually wire this out. So if we save and check our schematic, oh gosh, now we have more warnings. So we have a lot of stuff that is left floating and not really connected. So we have some of these inputs here that we know we're going to end up using later on, but then we also have these 2 body pins for this NMOS. So you might be tempted to just draw a wire to this point here, but that's actually not quite right. So this wire right here, this route is not connected to ground, so it is not connected to the substrate. It's connected to the drain of this next transistor. So we actually have to have a way of connecting these 2 together. So that's something that we're going to keep in mind. Now, we're going to come back to this, but really quickly, I want to talk about sort of the workflow of working with cadence. So typically, whenever you're working with cadence, you want to abstract problems as much as you can. So you want to start small with very small cells, and then as they get larger and things become more and more integrated, you want to actually be able to work with these smaller cells to abstract or model a problem differently. So for example, if you're working on a very high density analog circuit with hundreds of amplifiers and ADCs and things like that, you don't want to have this all on one schematic with thousands of transistors all in one place. It'll get very confusing. So what you want to do is you want to maybe make an op-amp cell like what we're working with. Now for an op-amp cell, you're going to have actual outputs. So you're going to have pins, inputs, and outputs. You're going to have ways of connecting everything together, and you have to make it as general as possible. So in order for us to make this into a symbol or into a cell that we can use for future schematics or maybe test benches or things like that, we need to actually tell it what the inputs and outputs are. And the way that we do that is by using pins. So in order to bring up the pin menu, we simply press P. So P will bring up a pin, or you can go to Create, and then you can go to Pin here. Now, for the direction, I'm just going to leave it as input, output. That way we can be a little bit general. And for the names, I'm going to start off, if we take a look at our schematic here, we're going to have a VDD. So remember, we're going to be able to apply power to our pin. This could be 5 volts, it could be 3.3 volts, it could be whatever. So we want to make sure that we have a VDD pin. We want to make sure that we have a ground pin because this VDD and ground is going to come from outside of this cell. And then we're also going to have our 2 inputs. So we're going to have VN plus, VN minus, and then this I bias. So typically you would want to create this bias on chip, but for this cell, we're just going to leave an I bias value. So we're going to have I bias, VN plus, VN minus, VDD, and ground. And we're going to make all of those pins. So if we go back to our schematic window and we press P, let's press escape and then P again so we can bring up the menu. Let's start off with VN plus, and then I can hit space and then do VN minus. And what this will do is it'll actually start with the first one. It'll lay down the first pin. And then once we lay it down, it'll move on to the second one. It'll delete this value, move on to the next value. So we can actually list all the different ones that we want to. So we're going to start with VN plus and VN minus. Now taking a look at this schematic, remember we have VN plus going first. If we take a look at this schematic, we should be able to figure out which of these is the plus input and which of these is the minus input pretty easily. And all we have to do is count the number of inversions. So if we assume, let's assume that this is going to be our VN plus input. If we count the number of inversions, and inversions happen when you go from gate to drain, we're going to have 1 inversion here. We don't have an inversion through this one, but we will have an inversion through this second transistor. So we'll have 1 inversion, 2 inversions, and then to our output, we're going to have 1 last inversion. So that's 3 inversions. It's an odd number. This is actually our minus input. So if we check this input here, we'll have 1 inversion, 2 inversions. And those 2 inversions cancel each other out, so this ends up being an even number. So this right side is going to be our plus input. Now I'm going to pop back over to my pin menu. So as you might notice, it needs to be flipped. And if I flip it, click here, it creates a pin called VN plus. Now let's go back. I'll flip it one more time, and you can see it deleted VN plus, and now we're working with VN minus, and we can place VN minus at the minus input. Okay, so we have 3 more pins that we need to put, so let's go ahead and put I bias, and then I'm going to call this chip VDD and chip ground. Now, I'll talk a little bit more about why it's chip VDD and chip ground here in a moment, but really all it is because our power supply is typically not going to be made on chip. So our power is going to come from an external source, and because of that, we have to have a lot of wires, connections, and that inductance could actually cause some problems. So those parasitics could cause problems, so we're just going to have a chip VDD and a chip ground. So our I bias, click back over to our schematic. I'm going to place our I bias right here, and I'll make that connection in a moment. And then double check. We're working on chip VDD next, so chip VDD, and then chip ground. And I can finish, press W, open up my wiring tool, finish making these connections, make sure that everything is happy. Make sure that we actually got connected there. Okay, great. So then do the same thing for our chip VDD and our I bias. Now we should be able to save and check and see, oh, nope, we still have some warnings. Oh, I can see why we have warnings. So there is something that we're missing from our schematic. So our I bias is going to be a current mirror, and we don't have the diode connection. So let's move back over here, press W, add our diode connection. That should get rid of 3 errors. Now we still have 2 warnings left. And the reason for that is because we forgot to go back and add these body connections. So these bodies are left floating. It doesn't know what to account for here. So what we're going to do is we're first going to wire them together, because we know that the bodies or the substrate, they're going to be connected together regardless. Now we know that they're going to be connected to ground, so we could draw a wire all the way here from our ground, but that can get a little bit messy, right? And we don't want our schematic to be too messy. We want it to be easy to read. So what we can do is that we can actually assign a net to this term, or assign a name to this net that will automatically connect it to ground. And to do that, we can either go create and then wire name, or as you might have just seen, we can just press L, and that'll allow you to create a wire name. Now we want our wire name to match the wire name of the net we'd like to connect to, and in this case, since we added a chip ground pin, I need to go back and change that, but in this case, since we know it's going to be chip ground, we're going to call it chip ground. If I click back over, we can add a label here, and now if we save and check one more time, it's still going to give us an error. Oh, no, it's not going to give us an error. So now we can see that it's actually connected to chip ground. We just need to come down here, click on our pin, whoops, escape and Control D, click on our pin, press Q, and now we need to add an I, so it's actually chip ground. Make sure it's chip VDD up here as well. Okay, so now we can save and check, and now we have a pretty well done schematic. So what we haven't done yet is we have not made the sizes correct. So right now we're just starting off with the default sizes, and we need to go back and change them. So if we take a look at our schematic, we can get these sizes. Let's start off with M1 and M2 because they're going to sort of match because they have to be balanced. So if we look at M1 and M2, the 2 input NMOS transistors, their W over L is going to be 32 over 1, and that's approximately going to be 7.95 times 4 over 1.05. And we'll talk about this here in a moment. So for these transistors, if we wanted them to be actually 32 micrometers over 1 micrometer, that's actually going to cause it to be a really long and skinny transistor. And that can cause some issues. The longer that a transistor is, the more physical space it's going to end up taking up on your on the actual layout. And that means that if there's some sort of variation in the process or in the manufacturing of the substrate, that those changes could be amplified. So we want our transistors to be as small as possible. That way, in a local area, the substrate and the properties are as similar as possible, and they're going to exhibit the same properties. So we want to try and keep this as small as possible. And the way that we can do that is by actually having multiple transistors in parallel. So that explains this 7.95 times 4. So if we take a look at, let's select, make sure I'm connected here. So if we select N3 and N4, and we have to hit Control to select both of them, or click Shift to select both of them. So if I click one, hold Shift, and click the other, we can select both, and then press Q to open up this menu. So if we press Q to open up this menu, we can see that we can change our width and our length from before, And we don't want to make this 32 micrometers. So if we make this 32 micrometers and then 1.05 micrometers, like we said, this is going to create a very long transistor. So what we can do is that we know that 32 is pretty much 8 times 4. So we can make this 7.95 micrometers. And then up here, we can actually change the multiplier to be 4. So if we change the multiplier to be 4, we can press OK. And we have 7.95, or 7.95 width, 1.05 length. And let's double check, make sure that that matches. So for M1 and M2, 7.95 and 1.05, except now we have 4 of these transistors in parallel. So we have 7.95 times 4. So having transistors in parallel essentially just means that we're going to have 4 times the current, which equates to having a 32 micrometer by 1 micrometer. So that is how we can actually make this M1 and M2. Now you'll notice that I only changed this one transistor here. So if I open up the properties menu again, and instead, if I go to apply to, instead of only current, if I click all selected, what we will see is that whenever I press apply, now it changes both of these transistors that we have selected. So that makes it go a little bit faster. So we'll do the same thing for the PMOS because we know that they're going to be balanced. So we'll click and then shift click the other. Q to open up their properties, and then we're going to take a look again. So M3 and M4, they're going to be 16 by 1, and that's still a little bit long, so we're going to make that 7.95 by 2. So there's going to be 2 transistors, the multiplier is going to be 2, and then the sizes are going to be 7.95 width, 1.05 length. So let's change this again. So we'll have 7.95 micrometer width, and then 1.05 micrometer length. And then what's important, multiplier has to be 2. If we apply, check our schematic again. So now we're actually defaulting to all selected, so we didn't have to go back and change that. Now we can actually start changing everything else. So let's see if there's any similarities that we can see. So we know that M8 and M5, oops, no, they're not. M7 and M5 both have this same value. So they're both going to be 32 by 2, so we can make sure that they're both NMOS, M5 and M7. So they're both 32 by 32, or 32 by 2, so we can actually select those together. And let's double check M5 and M7, so that'll be this transistor and this transistor. Open up their properties. It'll be 7.95 micrometers, and then 1.05 micrometers. And the multiplier for these, we want to get to 32. So if we are at 8 right now, just about, we want to get to 32, we need a multiplier of 4. So let's apply, make sure that it worked on both. Okay. Oops, and I accidentally messed up, and I put 1.05 instead of the 2 value that we needed. So let's change this to 2 micrometers, and it automatically changes it to 1.95. And let's make sure that they both have it. Great, so they both have it. So now both of these are 7.95 width, 1.95 length, and the multiplier is 4. Let's check M6 now. So M6, that's going to be 8 by 2. So what we're going to do is we don't actually have to have any multiplier for this one. We're going to make this 8 micrometers in width, 2 micrometers in length. And that's M6. That'll be this transistor here. So let's make it 8 micrometers and then 2 micrometers. Double check, make sure that's what we were actually doing. 8 micrometers and 2 micrometers. Okay. Now we have to make sure we press OK. And we have no multiplier here, so it doesn't show up that M number underneath it. So we have no multiplier. And now there's only one more that we have to change. So let's check what M8 needs to be. M8 is going to be 32 divided by 1. So we've seen before that's going to be 8 times 4 divided by 1. So let's change this one over here. Press Control D to make sure I unselect everything. Oh, press Q. So if we change this to 8 micrometers, by, is it 1 or 2? It was 1. Okay, so we'll do 1 micrometer. And then our multiplier here is going to be 4. Double check. Just make sure one last time. Okay. So now it looks like we've got a good schematic. If we save and check, then we can actually see that there are no errors, and it looks like we've got all of our materials, or all of our values correct. So now, we've actually got this schematic working well. But if we want to integrate this with a larger system, like maybe this is going to be one op amp and a larger analog circuit, then we are going to want a way of abstracting it. And the way that we can abstract it, it's kind of like saying these NMOSs here, we don't actually look at the physical layout or the connections of doped layers or anything like that. We actually just look at this symbol. So we're going to create a symbol for this schematic. Now the way that we can do that, you can make your own from scratch, but Cadence has a built-in way of making this. So what we're going to do is we're going to go to Create. We're going to click Cell View, and then from Cell View. So we're going to make a cell view from this existing cell view that we have. Now it's going to ask the cell view from, so we're going to tell it the cell view that we want to make. So we have an op amp, it's a schematic, and we want to make a symbol. And its type is going to be schematic symbol. Now we're just going to press OK. It's going to ask us a little bit about where we want these pins. And since we kind of know what we're going to end up making, or at least I know what we're going to kind of end up making, we're going to make a regular op amp symbol. We can guess where some of these pins are going to go. So our left pins are typically where we're going to want our inputs. So that's going to be VN plus and VN minus. So I'm going to highlight these, Control X, and move them to the left. Our top pins, I'm going to want chip ground. I'm going to want it to be on the bottom. Ground is typically on the bottom. And then I bias. I bias is also going to be an input. But because of the way that I'm thinking about wanting this problem, I'm actually going to put this down here on the bottom. Now, I've gotten to this point and realized I've made another mistake. So if we take a look here, we can see that we don't have any right pins, and that's where we said, generally, I want my outputs. And that means that I've forgotten my output pin. So we're going to have this be our output here. I'm going to make a little wire stub, and then press P to add a pin. I'll go ahead and flip it this way because I know I'm going to want it on the output, and I'll just call this V out. We come back over here, we can add our V out. Now we can do the same thing again, create, cell view, from cell view, leave all this the same. Now we get to do this again. So VN plus and VN minus, we said we want on the left. We want our V out on the right. Our top pins, we only want chip VDD, and I want to have my chip ground and I bias on the bottom, just because that's the way I'm imagining this symbol. Oops, I shouldn't have copied, I should have deleted. So we're going to have our chip ground and our I bias on the bottom, chip VDD on top, and then our right pins V out, left pins are inputs. So let's press OK, and then it will actually start us off with this little symbol. So now we've already got ourselves a symbol, but this doesn't exactly look like an op amp, right? If we looked at this, we know that this doesn't quite look like an op amp. So it also sets us up with some little things like this part name and the instance name that'll make our life a little bit easier later on. But what we want to do is we want to make this look a little bit more like an op amp. So I'm going to create a shape, and I'm just going to do a line. So if I just click line, now the draw mode is going to let me go at any angle that I want to, but I'm going to start here from the top, draw a line all the way down, and then to make it look like an op amp, I'm going to bring it over to the midpoint and then bring it right back. So now we've got ourselves this triangle, and we can get rid of these outside edges here. Now this is already looking a little bit more like an op amp. Now it looks like maybe it's not exactly symmetrical, so maybe if I hit S to stretch, maybe I can move this corner up slightly. Looks like I can. Okay, maybe that looks a little bit more symmetrical. And now I'm going to move, and I'm going to select this V out pin. So if I select this V out pin and then click, I can scooch it down just a touch, maybe scooch this text a little bit more inside, that way I can see it. And now it's starting to look maybe a little bit more like an op amp, although I'm not exactly sure if it's still symmetric. But it's okay, it doesn't matter, it's not the most important thing in the world. So now I can do the same thing just to make it look a little bit better, so I can press move and select our VN minus, move it a little bit further up just to make sure that it doesn't get too crowded. Move this guy down a little bit. Now I want our chip VDD, I don't want that large space to be there, so I'm just going to move it a little bit closer. We might have trouble getting it to lay exactly on that line, but we can get it pretty close. And then we're going to do the same thing with chip ground. Bring it as close as we can. Scooch it over one more just so that it can match. Oops. I guess that goes to show that maybe this isn't exactly symmetric. Maybe we can scooch this corner down a little bit more again. It looks like we're just not gonna have this issue. Okay, now for our eye bias, like I said, the symbol isn't the most important thing, but it is something that you want to try and make look good. You know, just like everything, you want to make sure it has your best effort in it. And I'm going to move our eye bias over here because we're going to have a bias current in our test bench, and I'm going to have this connection just down here on the bottom. Now I have our VN minus on the top. That's generally how I like to see op amps, but you could flip these if you wanted to. But now we've got a pretty good looking op amp symbol. Now this little red box, that's actually going to be the bounds for this symbol, so if something gets too close, it'll let you know. So I'm going to just stretch these a little bit further down because I want our bounds to actually be, to encompass everything and not give us some errors in the future. Now we can save and check this, and we can actually see that we didn't get any errors. We can check our CIW window and see that cross-view check completed with no errors. So whenever we save and check here, it's actually going to make sure that we have all the same pins on our symbol that we do on our schematic. Now, what we can see is that this, we're having a little bit of trouble seeing, so I'm just going to grab it, rotate it, and then I'm going to move it just down here. That way we can see it a little bit better. Deselect everything, click this one, move it, and let's rotate it. And we're going to move it here again. So now we can maybe read things a little bit better. Save and check one more time. And now we've actually got our symbol. Now I'm going to close out of this window. I'm going to leave this schematic window open. But if we take a look at our library, what we can see is that under the new library that we made, we still have our op amp cell, but now we actually have two different views. So we have our schematic view that we've worked with previously, and we have this symbol view. And this symbol view is what we just made, but this symbol view is what's going to allow us to actually integrate this stuff into some higher level designs. And that's actually what we're going to take a look at right now. So I'm going to go ahead and close out that view there. And then what you can see is that we want to create a symbol, which we've already done, and then make a test bench schematic. So we've integrated this into an actual schematic, and we've made our cell. We've made our cell for this differential amplifier here. But now we want to make it into a test bench schematic. So if you imagine, if you actually, for example, ordered this IC, if you actually ordered this circuit, you would have the bare dies, and you would have to connect those to a package in order to connect it to a test bench. And that's going to include some more parasitics. Or like we said before, if you wanted to integrate this into a larger system, you would need, you would need multiple different cells, and then those would typically have an external power supply. So having this view here, where it's sort of abstracted and we just have these pins to connect to other circuits, makes it a little bit easier for us. So I'm going to close this, and we said that we want to make a test bench schematic. So this test bench schematic, we don't want to make it on our op amp cell because this test bench schematic isn't going to be the same as the schematic that we've already made. So we're going to make a new cell view. So I'm going to call this one op amp underscore TB for test bench. It's still going to be a schematic, and we're still going to use the same schematics, but this one is going to be slightly different. So now we have our blank schematic window. If we click here, press I, instead of working with analog parts, if we go to the library that we just made, ECE 2, we can actually go to the op amp cell, and since we made a symbol, we can place this symbol inside of this schematic. So we can place our op amp symbol inside the schematic, and it'll tell us its name is op amp, instance name is I0, but we can actually use this to run some tests or run some simulations. So that's what we're going to be doing. Now, what you'll notice is that if I wanted to, for example, take a quick look here, I could view, after I select it, I can click view, and let's see. So I can click view, check, perhaps it's under hierarchy. Oh, no. So let's just forget about that. So if we click it and we press Shift X, it'll actually allow us to view the schematic. So it'll allow us to descend into this symbol here and actually view it. So now this is our, this is our actual op amp cell in the same window, and we can see, we can see the actual schematic that is down below. And if we get tired of this and want to go back, we can just press B. Now, what we can see is that inside of this cell, we didn't use any ideal voltage sources, current sources, or anything like that, because those ideal voltage sources and current sources can't be realized on chip. So this is only stuff that can be realized on chip, and we're going to include the ideal stuff outside, because that could be something like our power supply, benchtop power supply, sources, or things like that. So we're going to include that here. So let's start off with our power supply. So if I press I, now instead of the ECE EDA2 library, we're just going to go to analog lib. And then for the cell, we're going to want a couple of voltage sources. So I'm going to do VDC. For this first one, we're going to make this our VDD. So I'm just going to call it VDD for its DC voltage. And we're going to press it. Let's just set it here so it's sort of out of the way. So that's going to be our V0. And let's just double check and make sure that it got everything. It did not, so it's a good thing we double checked. So let's set this VDD and apply. Now, whenever we are making a test bench for this, what we're going to want to do, we're going to want to connect the amplifier output back to its negative input to form a unit gain voltage buffer. So we are going to, let's go ahead and just connect the output back to the input. So I'm going to make it go up a little bit higher just to make it a little bit easier for us. So we're going to connect it back to the input here. So now Vn minus is connected to the output. And then our Vn plus, we are going to need a voltage source here as well. So what I'll do is I'm going to call this Vin, actually we'll just call it VDC. So we'll call it VDC volts, and we're just going to click it right here. Now we're going to wire this. And then we know that we are going to add in some parasitics. So like we mentioned, whenever you actually have bond wires connecting a package or connecting your test bench to the actual silicon itself, that's going to add some inductance. So what we're going to do is we're just going to add in an ideal inductor. So if we go to analog lib and do IND for inductor, and let's just leave it at 1 nanohenry for now because it's not going to impact our stuff too much, but it is important to add. We can rotate it. And we're going to have a bond wire to connect chip VDD and chip ground. So let's go ahead and wire these together. And these are going to be our chip VDD and our chip ground, respectively. Oh, we've got to make sure that it actually gets connected. Now, as for the same way as we did before, we're just going to press L and give it a name. So I'm going to do chip VDD and chip ground. Press enter to hide it. And then add a chip VDD and a chip ground label. Now right now this chip VDD and chip ground is not connected to anything because we haven't told it what to connect to yet. And instead of routing things all over the place, I'm just going to add little connections there and do L again, chip VDD and chip ground. So we can add our chip VDD and our chip ground. Okay, now we still have some unconnected stuff. What we can also see is that we don't have a ground symbol yet, so we don't have a global ground. So let's go ahead and add our analog library, that ground symbol. So we're going to add a few of those. One of those is going to connect to the bottom of our VDD. We're going to connect one to the bottom of our input voltage. And then I'm going to go ahead and add one here. So let's just assume that we can have an ideal current source, and we're going to connect it to I bias. Now, if we take a look in here, we can see that the current must be going into I bias in order for this to work properly. So we need to keep that in mind whenever we're actually making our ideal current source. So if we go to IDC, looking for a symbol, if we were to set it this way, you can see the arrows pointing down, this would be wrong because now our current is leaving the chip. We want to flip it upside down, have that current going into the chip. And then I'm going to move this ground connection up just to keep everything tidy, and then select our I bias, and let's call its DC current I bias. And I'm going to move this chip ground over here. Oops, not that. I'm going to move this chip ground just a little bit so that we can make sure that we can always see our stuff. So we can call this chip ground up here. It's still going to attach that label to the point. You can see that little line that it has connecting it to the wire. So it's still labeling it chip ground. We're just moving that label around. Now this looks okay. Let's save and check. So if we save and check, we can see that we're not getting any major errors, and we've got our test bench schematic working well. So now we have a pretty versatile schematic. So down here in the actual analog IC design, we have a schematic that we could realize on chip, entirely on chip without any ideal components or anything like that, using realistic values. And then if we go back up, we're actually able to test this with real life parasitics and things like that. So we're actually able to have a test bench. Now we can actually start simulating this circuit the same way that we did before. So let's start off by launching ADEL, and we're going to launch it from this test bench view because we want it to be attached to the test bench. So let's do a little bit of that setup. So if we go to our initial setup, we can change the simulator. We want our simulator to be Spectre. Press OK. And now we can go to setup again. We need to find the model libraries. So if we click here to add model file, click the three dots. Under model, we have NTT. And since we have NMOS and PMOS, we also need to include PTT. So let's press OK. And now, let's just double check and see. We can actually, oops, that's not what I wanted. So we can actually check this really quickly. Let's go ahead and bring in our variables. So for our I bias, we check over here. Our I bias is 10 microamps, so we'll make this 10 micro. Our VDC, that's going to be the input voltage here. VDC1 and VDC2, those are set to be 2 volts in this case. And then our VDD is set to 5. So now if we take a look at just a quick DC analysis. So we're going to do a DC analysis, something that we're familiar with. We're not going to sweep any variables. We're just going to do a quick DC analysis and have it annotate the DC operating point. So we can run the simulation, see if it actually runs all the way through. And it looks like it's run okay. So we can results, annotate DC node voltages. And if we take a look at our schematic, at our test bench schematic, we can see some of these DC node voltages. And we can even pop inside. And if I just hit X, if I know I'm not going to want to edit, if I just hit X, I can actually open this for read, so I make sure that I don't edit anything. If I pop inside, we can see that all the DC node voltages are annotated. So the DC node voltages are all annotated. We can tell fairly quickly by looking at it that everything seems to be acting in the active region and seems to be working happily and everything like that. So that's a good sign to have at the very beginning. So let's press B, pop back out of here. Now we can maybe start doing some other simulations. So if we take a look at our DC simulation and see that everything is working well, we can take a look at our other simulations. But maybe let's do one quick analysis, one quick DC sweep, just to see how this thing operates. So for now, we're actually going to sweep a design variable. And I want to sweep in our VDC, our DC input. And we'll go all the way from 0 to, call it VDD. Well, let's just set it to 5 because I'm not sure if VDD will work exactly. So let's run this analysis just to get a sense of how our circuit is working. So if we go to results, direct plot, and main form, we have our plot window here, and let's see how the output voltage changes as a function of the input voltage. So we're going to select a net. The one we want to see on our schematic is our output voltage here. And let's take a look. So what we can see is that in the very beginning, whenever our input DC voltage is really low, we see this nonlinear portion in the very beginning. But then as we get to our normal operating point here, our input voltage seems to match our output voltage. And once we get closer to the end, once we start to saturate things, our input voltage and our output voltage start to not match again. So we have these sort of non-linearities on the input and output whenever things stop working in the active region, which is sort of what we expect. So this again sort of confirms the operation for this schematic with something that we already know, how to do. So let's go ahead and disable this sweep because that's not really what we're trying to do here today. And let's start talking about the next simulations that we want to do. So if we take a look at this paper, we can see that we want to simulate the loop gain, closed loop gain, and closed loop output resistance. Okay. Now we're also in the future going to want to report phase margin. So we're going to want to make sure our phase margin is greater than 65 degrees, and then minimize compensation, capacitor size, and things like that, okay? So what we're going to do is we're going to figure out how to simulate this loop gain first using a stability simulation. So for our stability simulation, it uses some pretty cool techniques in order to actually figure out the loop gain and things like that. But we need to make a quick change to our test bench schematic. So what we need is that we need a way of measuring voltage and current inside the actual feedback loop, but we don't want it to impact, we don't want it to impact our circuit itself. So the way that we can actually do that is that we can give it a probe point using a DC voltage. So we're going to connect a DC voltage in series with this feedback path. Now, if we want a DC voltage in series without it actually impacting anything, then we need to set the DC voltage to be 0. So it's pretty much a short circuit, and we can place it in this feedback path, break the loop here. So now we have a DC voltage of 0, so it's almost like it's not even there. It's pretty much just a short circuit, but this gives us a point to click and probe our feedback loop to actually measure the loop gain and measure the stability. So I'll save and check again. And if we pop over to ADEL once more, we're going to add a new analysis. It's going to be a stability STB analysis, and we're going to want to sweep frequency. And the sweep, let's go from 1 hertz all the way to 1 gigahertz. So we're going to go from 1 hertz to 1 gigahertz, and it's asking for our probe instance or terminal. We're going to click select, go to our schematic, and then click that voltage source there. And you'll notice it didn't highlight, which is a good sign. Now I can say we've got /V2. So we could actually just type this in if we wanted to. We don't have to go through the selection, but that does make it a little bit easier. Now let's hit OK. So if we run the simulation again, we can actually check and see our loop gain and see how it behaves for our feedback and our stability. Okay, so we can see our loop gain. We can figure out, how it's actually going to be impacting our circuit. So it looks like, double check and make sure that everything worked well. Yep, so it looks like our stability analysis completed. We can go back to results, direct plot, and we can go to main form. It's asking us again about this. So on this plot, now we have a stability analysis here that we can select from. So we can either plot loop gain, phase margin, stability summary, stuff like that. For now, let's just do loop gain. Now it's asking if we want just the magnitude, the phase, or both. We want both of them. The magnitude modifier, I'm going to leave it at dB20 since this is voltage, and we're going to add it to our outputs. We have to press plot. So if we press the plot button here, we can actually see our magnitude and phase. So the pink corresponds to the magnitude, and we can see that it starts off very high at 79.349 dB, and then it doesn't cross 0 until this point, till about 360-ish megahertz. Now, it's tough for us to zoom in and exactly see where exactly it crosses, but what we might want is a marker. So if I click on our line here and press M, that'll add a marker that I'm actually able to move around. Now, I don't want to have to drag it exactly where it needs to go, so what I can do is I can click on our marker, press Q, and then we can actually tell it the position. So if we tell it that it's attached to this trace, we can actually select by Y mode, and we can tell it we want it to be at the point where it crosses 0 dB. Now if we press apply, we can see that it actually moves itself over to 376.733 megahertz, and that's where it's equal to 0 dB. Now, to see our phase margin, I'm going to scoot this up a little bit more. To see our phase margin, what we want to do, I guess it would be a good idea to split these two in the meantime. So let's split them. We still have our marker here pointing at 0 dB. To calculate our phase margin manually, what we want to do is we want to add a marker to our phase as well. Except this time we know the gain crossover point. So I'm going to click on this marker, press Q. Oh, looks like I have the window already up. And now, instead of going to Y mode, we want to move it to its X mode. So we know the frequency, we want to move it to that frequency and measure the phase. And that frequency is 376.733 megahertz. If we press apply, oh goodness, It seems to mess up like this every once in a while, and I haven't figured out why yet. So let's add another one. Press Q. X mode, 376.733 megahertz. Okay. Well, that's just not right. So if we maybe scooch it ourselves, we can get it pretty close to this point and see that at this 376 point, we are well below 0 degrees. So we've gotten more than enough positive feedback for this amplifier to be unstable. Now, at this point, I am somewhat cheating here because if you come back to the direct plot window, which I guess I've closed already, if we go to direct plot and main form, if we click on phase margin, if we have a positive phase margin, it will actually show up here. Now, in previous versions, it would tell you the negative phase margin, but in this one, whenever it's negative, it's actually going to kick back this error. It's going to say, oh, PM metric is not found because your PM is negative, and that just means you're unstable. And if you look closer at this simulation output window, it'll say, can't obtain phase margin and gain margin because the circuit is a positive feedback system and unstable. So it's pretty much found that we are unstable, and it's unable to tell us the phase margin itself. So we need to add some compensation for this. So let's go ahead and pop down here, and we can add some compensation. So I'm going to go Shift X because I actually want to edit it. And we want to add a Miller compensation capacitor. So I'm going to scooch, oops, don't want to use M, I want to use S. So I'm going to stretch this pin, scooch it over just a little bit. I'm going to move this wire over as well so it's not kicking out too much. And we're going to add ourselves a capacitor instance. So if we go to analog lid and cap, we can start off with a 1 picofarad capacitance. And we're going to add this guy in parallel from input to output on our second stage. And this should hopefully help us with stability and maybe helping us improve our phase margin. Now we do have an error somewhere. Oh, so you can see that this error is a little bit misunderstanding. So warning, solder dot on crossover at this point. So if you want to get rid of this error, you can simply S, move this a little bit further. Oops, that's not what I meant to do. Move this, undo, press U to undo, press S to stretch it, move it a little bit upwards, and for some reason it doesn't complain about that as much. So now we actually have a clean schematic. We can press B to move back, save and check just one more time, and let's run our simulation once again. Take a look at our outputs. Let's see how these outputs will change. So you can see that now we've gotten a little bit of change in our phase. So if we take a look at this yellow curve, which is going to be our loop gain, we can see that it crosses over much sooner now. So it's going to cross over. Let's go ahead and do this the correct way. Add a marker and see exactly where it crosses over. So if I Q, have it go by Y mode to 0 dB. Zero, apply. Oops, it looks like I accidentally pressed F1, so it opened up cadence help. So we are actually able to see exactly where it crosses. So now its crossover point is at 122.533 megahertz. And if we take a look at the loop phase, around this point, we're still below this value. So what we actually want to do is, per this sheet here, we want to have a compensation capacitor and resistor. So we want to have an R and a C. So let's go back to our schematic. We only added a C, so this time we're going to descend. And this time we're going to add an R as well. So for our cell, we're going to do res. Let's just start off with 1K. So let's start off with a default value of 1K. Make sure everything is wired up well. Save and check. So once we're good, we can press B. Save and check here one more time. And now, oops, let's go back to our ADE window, run the simulation just to see how we're doing. Now, what we can see is that after running this simulation, let's check our loop gain once again. our loop gain crosses over in between 60 and 80, and we can tell really quickly between 60 and 80, now we might be getting really close to where we actually have a positive phase margin. But we don't necessarily want to continue this cycle of just changing small things and then seeing how it reacts. We might want to automate it a little bit more or make it a little bit easier for us to see these results quickly. So I'm going to pop down again, and I'm actually going to change the values of this resistor and capacitor. So I'm going to come over here, click on our resistor, and I'm going to change this to Rm for R Miller, and then click on our capacitor, change it to Cm for C Miller. Whoopsies. So click, opened up our delete tool on accident. So I'm going to come over here, change it to Cm, save and check, and return, save and check. And then let's go over to our ADEL, bring in those new variables. For our Cm, let's start off with 1 pico and 1 K, what we just had before. And now we can actually use parametric analysis. Let's see, results or tools, parametric analysis, and we can actually use parametric analysis to figure out the best situation. So we want to minimize the compensation capacitor. So we want to minimize the capacitor size. So we don't care as much about the resistor size. It is something to keep in mind, but we want to minimize the size of our capacitor. So let's start off with a sweep, excuse me. Let's start off with a parametric analysis. Let's see, where is that window? Oh, here we are. And what we're going to sweep is we are going to sweep our Miller resistance, so our feedback resistor. And let's start with 1K to 10K. Let's make it do 10 total steps. And we can run this. And now what we should be able to see is that we should actually be able to see some value for phase margin whenever we plot. Once it finishes running, we can check our visualization window, and we can see that for our loop gain phase, we have a bunch of different values, 10 different curves. For our loop gain itself, we have 10 different curves. But we can add, we can go back to our ADEL window, do results, direct plot in main form. Now, since we have a sweep variable, we can actually plot our phase margin versus that sweep variable. So if we come back down here, let's move this to a new sub window. So if we click, so if we click on this graph here, here we go. We can click move to new sub window and then change this size just a little bit. Okay. So let's just take a look at this phase margin for now. So what we can see is that for different values of this resistor, we actually have very different values of phase margin, right? So we have a bunch of different values with just a 1 picofarad capacitor. So we've kept our capacitance the same, but we can sweep for different values of this resistor to maybe maximize our phase margin. So if we want to keep our resistor as small as possible, but still have a phase margin of 65 degrees, then we could go with the value of about 3.3K. You want to do a little bit better analysis than I'm doing right now, but you could go with about 3.3K and get a phase margin in the realm of 65 degrees. So using parametric analysis can really help you figure out the best case scenario or maybe the minimum value of a resistor that you would need. Okay, so we figured out how to plot loop gain, how to figure out phase margin. So let's take a look at our sheet one last time. So we've done loop gain and we figured out phase margin. So for the compensation capacitor and resistor, I would recommend trying to minimize the capacitor size, so maybe going below 1 picofarads, because as you can see, we have a lot of headroom on phase margin. So in this case, we have phase margin of 92.9 degrees. So what you can do is that you can actually maybe change your capacitance to be much smaller, maybe in the femtofarads, and then see maybe what values of resistance would give you this ideal phase margin. So you can actually minimize the size of your capacitor, which I didn't do here. So we figured out how to do loop gain. Now let's figure out how to do closed loop gain and closed loop output resistance. So if we pop back over to our design window here, and we take a look at our VDC. What we can see is that if we click on the properties of VDC here, what are we looking at? it might be adding probes to our output. So let's check it here. Okay, so let's check back here, save and check. That is strange. Let's escape. I must have a tool open. There we go. So if we press escape, I guess I had some hidden tool open. We can see on the properties for this source that we have something called an AC magnitude as well. So this actually lets us only look at AC analysis, which is really good for us to help figure out our gain. So for our AC magnitude, I'm actually just going to set this to 1 volt. Now, you might be saying that this is a super large value. So if we have 1 volt on the input, that's going to give us 1 volt on the output, and we could swing into the nonlinear regions on accident. But what this simulation does is that it actually looks at the AC response for just a very small perturbation. So it kind of linearizes the circuit, looks at the AC response for a very small signal, and then gives us the AC response relative to this input excitation. So this relative voltage here. So if we have 1 volt on the input and we measure, for example, 10 volts on the output at a certain frequency, then we know our gain is 10. So it makes it a little bit easier for us to actually measure the gain at certain spots. So we're going to press OK, save and check. Now we need to add a new analysis. So this isn't stability and it's not going to be DC either. So we have to choose a new analysis, and we are actually going to do AC analysis. So we're going to sweep our frequency. We're going to go from that same 1 hertz to 1 gigahertz. And we're not going to do any sort of specialized analysis or anything like that. We're just going to press OK. So we can run the simulation. Run the simulation. We have our loop gain and our loop phase. You might notice that the phase margin disappeared, but it is actually down here still. So with the current values of capacitance, let's see, I'm going to go ahead and change this to 5K because we know that that gave us a pretty good value for phase margin. And we can run this one more time, and what we'll see is that our phase margin is actually listed down here. So since it's just a single point, we're not doing a parametric analysis, it's just going to be listed down here. But our loop gain and phase is going to be output. So because I don't, well, actually, we'll leave it here for now. We can actually do results, direct plot, and main forms to see our AC results. So we want to make sure we click AC. Now you can see it's going to ask us for a voltage, a current, or GD. We want to measure a voltage. And we want to see the magnitude in dB20. Well, actually, let's just leave, yeah, let's do dB20. Why not? And we're going to add this to our outputs, and we need to select the net. So we want to measure the gain from the input to the output. So we're going to click on the output here. And now if we take a look at our results window, we can see, we'll go ahead and split this one to be by itself. Let's see. There we go. So we'll split this one to be by itself. And what we can see is that our gain is pretty much at 0 dB. It's got this minus 506 micro dB something here, but that's pretty much 0 dB. And then it starts to really drop off. Our 3 dB point is at about 60-ish megahertz or so. So this is our actual closed loop gain. So after we've closed the loop, we're measuring our output voltage versus our input voltage. And for a unity gain buffer, we expect it to be pretty much 0 dB from input to output regardless. So just as an experiment, let's actually take a look and see what happens if we, oops, make sure we escape out of that. If we change this value from 1 volt to, oh, not 12 volts, goodness. Let's change it to 2 volts. Save and check, and then run again. Let's see what happens to this output here. So now our AC output has gone all the way up to 6 dB. So that doesn't mean that we have 6 dB of gain. That's saying that if we do 20 times the log of this output voltage here, it gives us 6 dB. And the reason for that is only because we changed this AC magnitude in the beginning. That's why it's important for us to keep it at 1 volt. That way, if we're measuring the closed loop gain, we can get a better sense of the actual gain that we're getting. Let's run this one more time and make sure that everything is back the way we expect it to be. Okay. Yes, so now we're back at just about 0 dB. We can split this one. Let's see. Let's move to a new sub-window. Okay, so now we can see our closed loop gain and our open loop gain in phase. Okay, so now we've gotten our, let's go look back at our sheet. We've gotten the loop gain, closed loop gain. We've looked at the phase margin and the compensation capacitor and resistor. Loop gain, compensated phase margin on the graph. Okay, so the last thing that we're going to be taking a look at is the closed loop output resistance. So we're going to be taking a look at closed loop output resistance. Now, there's lots of different ways that you could do that. Some of them involve actually, if we're going to measure this versus frequency, some of them will actually involve adding something like a voltage source connected to the output with a large enough isolation, so like something like a capacitor between the two, to actually measure what happens or what kind of current in we have at various AC frequencies. But we don't want to have to do all of that stuff. We want to be able to make our lives as easy as possible. And the way that we can do that is actually using XF analysis. And that stands for transfer function analysis. So XF analysis requires a couple of things. So we also need another probe. Now, this probe that we're going to have is actually going to be a current probe. It's going to be a current source input because we want this probe to go in parallel with our output. And if we want something in parallel with our output but to have no effect, it's going to be a current source with zero current. So if we press I here, go back to IDC here, and we're going to go ahead and set the DC current to be 0 amps. And we can just set that right here. Now we want this to be connected to ground. And we can save and check, hopefully get no errors. And let's run our simulation just one more time to make sure that nothing major changes. So if we see a major change, then we know that maybe we did something wrong, but now it looks like we still have everything just how we want it to be. So let's move this to a new sub window again. Yeah, everything looks pretty much exactly the same as it did before. So for the XF analysis, what we're going to do, we have to, again, add a new analysis. So we're going to add XF, and this is going to be measuring the transfer function at different frequencies. So we're going to sweep the frequency, do the same 1 hertz to 1 gigahertz. Oops. Now, our output, we're actually going to be using a probe, and the output probe instance is going to be select. It's going to be this one here. So it's not going to be adding anything to our output, impacting our output, but it will actually let us do what we want it to do. So we need to finish setting this up. I need to close some windows as well. So we've got our probe selected. We want to enable it. I'm going to go ahead and close our parametric analysis and our component selection window. Now, if we run our analysis, we should still get the same thing that we got before. Great. So we have the same thing that we had before, and we're going to results, direct plot, main form. And this is going to be for XF analysis. Now, transfer function, we could use this to measure voltage gain. So we can measure the voltage gain, voltage gain on the output versus a voltage on the input, or we can measure transimpedance. So what transimpedance is going to do is it's going to actually measure the voltage created, it's going to measure the voltage created by an input current. So if we put in a small input current, it's going to measure that voltage and use that to figure out what's called the transimpedance. So typically this would be for something like a transimpedance amplifier where you have a small input current and you want to change that into a larger output voltage, give it some gain. But for us, we can actually use this to measure output resistance. So if we have this small current probe here, it's going to use this pretty much as a current source. And it's going to say, if I insert a small current in this direction, it's going to measure the output at this probe, which is at the same spot, and it's going to tell us the transimpedance, which pretty much equates to the output resistance. So let's look at the transimpedance, and we are only going to care about the magnitude in this case. We don't care about the real or imaginary parts. We just want to know how large the resistance is on the output. And it's asking us to select the current source. The current source we want is this one here. And now, on our visualization window, we should have a whole different, let's go ahead and try and move things around. So let's split them all, and we'll actually combine those two together. Now let's just go ahead and make this look a little bit better. So let's move this to a new sub window, move this one to a, oh, there it is. Move this to a new sub window as well. We'll split these two as well, just to make it somewhat even. Okay, so our loop gain and phase still look pretty much how we expect. That analysis hasn't changed. Our closed loop gain still looks good. And now we can actually see our output resistance. So as we can see, at very low frequencies, our output resistance is at about 30.252 volts per amp. And volts per amp, if you figure it out, is just ohms. So right now we have a 30.2 ohm output resistance. And if we continue up and up and up, we can see that that tends to increase quite a bit. It reaches its peak at 288 megahertz and then starts to decrease some more. So this is actually a way for us to measure our output resistance in this case. Okay, so this is a pretty good way to get started on this next homework. So it gives you a pretty good way of seeing how we can simulate loop gain and phase for stability, closed loop gain, how you can get phase, or actually let's take a look and make sure that phase margin is still here. So our phase margin is still 92.89, as well as getting all the stuff that you need set up. So as we mentioned before, if you want to get rid of this stuff, so we can actually, we come here, we can export this graph, which we saw in the previous video how to do, which makes it a little bit easier. You can also change the background color. You can change the thickness of these traces to make it a little bit easier to see. And then, as I mentioned before, you can also go through, use the parametric analysis tool to maybe further minimize the size of the compensation capacitor. Because right now it's still 1 picofarad and it can still definitely be smaller. Okay? So if you guys have any questions, please feel free to let me know, either in the comments or you can feel free to shoot me an email. Other than that, thank you guys for watching. Okay, so true to form, I did forget something that I needed to show you guys. So phase margin, the reason that we want it to be so high is because the circuits that we make aren't always going to be operating under ideal conditions. So for example, if we have maybe a change in VDD, that can definitely impact our phase margin. And if we have a change in VDD or a change in maybe the ambient temperature, all of those things can have a pretty bad impact on our phase margin. So we want to make sure that we design with enough headroom for there to be some non-idealities without it completely breaking our circuit. So for us to actually see this phase margin versus the change in temperature, what we can do is that we can, actually if we're only going to plot here, we can first take a look at our stability simulation once again. And if we are going to sweep our frequency, which is something that we want to do in order to actually determine our phase margin, what we're going to do is we can go to Tools, Parametric Analysis, and we can sweep the temperature pretty easily. So if we sweep our temperature, we can sweep it from maybe -20 to 120. And let's just say we want to do 10 steps again. And we can run this. It's going to take a little bit of time, but what we can see is we can actually see, in this case, how our phase margin changes whenever we change our temperature. So with this setup before, we had a phase margin of over 90 degrees, which is pretty good. But what we can see is that our phase margin works a little bit better whenever it's colder. So whenever it's cold, we seem to have a little bit better stability, but then as we increase in temperature, our phase margin starts to reduce. So if we only design for a phase margin of, say, 10 degrees, down here we've decreased by considerably more than 10 degrees. So if your chip gets too hot, it starts to oscillate and things like that. Now we can also, let's combine another sweep. So I'll add another column. Let's sweep our VDD. So if we sweep our VDD, let's say we go from 4.5 to 5.5 in 3 steps. So now we've got 3 steps on VDD, 10 steps on our temperature. It's going to be quite a few runs, but it's going to just keep plugging along, running all these, and then we should be able to see how our phase margin changes for a variety of VDDs. So we can maybe see in which case it's better and which case it's worse. And this is actually something that's pretty important for analog designers, because you want to make sure that your circuits work in a variety of conditions, not just say that you have to have this IC strapped to a liquid cooler 24/7. We want to make sure that it can get a little bit hot, have a little bit of wiggle room for maybe some non-idealities or things like that. So our simulation is done. Now what we can see is that for these values of VDD, for these high temperatures and lower values of VDD, our phase margin starts to decrease. So if, for example, we have our circuit connected to a battery or something like that, and over time that battery becomes discharged, that could also impact our phase margin. So this is something that's pretty important, and we've got to make sure that we account for, because we don't want to get all the way through the design of a circuit and then find out that at the very end it doesn't work how you expected it to because your phase margin wasn't good enough. So this is just something else that I wanted to show you, how you can include temperature in these sweeps themselves. It's a built-in variable, and how you can also combine it with a different simulation. So like I said, if you guys have any questions, please feel free to let me know. Other than that, thank you guys for watching.